Recorded. I have just started the recording. So kindly keep in mind this. Also, this is primarily to give opportunity for those who are not able to join us now to watch this final event later. Secondly, please mute your microphones. We do not want to. We want to have our speakers concentrated on their presentations. And when it comes to your cameras, you can close them. You don't have to close them however you want. But please, you can participate actively. This means that you have a chat box, and you can put your questions in the chat box, and we will address them at the end of our final event. Now, once more to say that we are here to have a demonstration of our knowledge lake management system. We will start first with Dimitris Skoutas, our project coordinator, giving a comprehensive overview of the comprehensive but concise overview of our STELAR project, which is, by the way, wrapping up on August 31st. Secondly, we will give the floor to Vasilis Samoladas, also from Athena Research Center. He will introduce us to the KLMS, and then Dimitrios will actually give a demo. So Dimitrios Petrou, also from Athena Research Center, will give a demo of this system. And since STELAR is a project that tested its results in real-world conditions, we will hear from our 3 pilots, and we are very happy to see their perspective and hear their perspective on this. And finally, we will have a short Q&A session at the end. Just to say that our leaders from the pilots are Babis Stanopoulos from Agrono, Solveig Blöcher from Vista, and Simone Parisi from Abaco. And with that, I think that I can give the floor to our coordinator, Dimitris.
Okay. Hello, and thank you very much, Julia, and thank you everyone for joining. I guess it would be better if I share the slides now so that I can go through the presentation. Just give me a second. So again, welcome to everyone. My name is Dimitris Skoutas. I'm a researcher at Athena Research Center and also the coordinator of the STELAR project. We will start with, as Julia said, a brief introduction to the project. And also, as Julia said, this is the final STELAR event. By final, this implies that there has also been a series of previous webinars concentrated more on the pilots, or in some cases, some joint webinars with other projects. Of course, in all cases, we had a brief introduction to the project to provide some context. So if some people from the audience have already attended previous events, I apologize for this repetition, but hopefully it is useful to give some context. So I will go quickly through some basic facts so that we have more time later on for the KLMS and especially for the demo, which is definitely by far the most interesting part. So regarding the project itself, the full title is Spatiotemporal Link Data Tools for the Agri-Food Data Space, and it is a European project funded under a call for technologies for data management. So our main focus here is tools for data management. So we're targeting data scientists and support them in the process of data collection, data preparation, workflow tracking, and so on. The project has a duration of 36 months, and we are actually very close to the end. It is completing its activities in about a month from now. And you can find more results in the project website. Also here you can see briefly the consortium comprising 9 partners, which are broadly categorized in 2 main categories. There are partners that lead the activities for developing the platform and the toolkit, which will be the main focus today, and also pilot partners that lead the use cases, conducting the evaluation of the platform and the tools. So just to say a few words about the challenges that we are trying to solve. So our focus is on data preparation. This is something very important, but also something that is often neglected and does not receive a lot of attention because usually the focus is more on machine learning and AI. However, in order to get good results when building AI applications or developing ML models, it is very important to have appropriate and high quality data. This involves a series of steps that typically start with data discovery, where someone needs to find appropriate data for a given task and possibly compare data sets from different sources to find out which data set or data sets are more suitable. Then typically there is a stage of data integration because in many cases you need to combine data from different sources. And again, this raises several problems and challenges like aligning different entity representations or dealing with differences in spatial or temporal resolutions and so on. And eventually, preparing the data for training a model, which involves challenges like data labeling. Often there is a scarcity of labels, and then there is a room for automated labeling techniques, for example. Also, dealing with detecting biases in the data and mitigating bias, or for example, if there is not much real data available, there are questions about how someone can generate synthetic data and use this for model training. These are the kind of challenges that we are dealing with in the project, and our vision is to develop, as we call it, a knowledge lake management system, KLMS, which supports fair and AI-ready data. This has two main pillars. On the one hand, the platform itself, which will also be the main focus here. And this platform contains some core components like a data catalog, a knowledge graph, a data repository, and so on, that helps data scientists to better manage their data sets, and also the metadata about the data sets, but also about the workflows to integrate this metadata and to provide better search functionalities. On the other hand, on top of this platform, we are building a toolkit that contains some predefined tools that we're developing in the project, which support different tasks like data description, data linking, and annotation. But of course, this is an extensible list, and other tools can be added. And the evaluation of the KLMS happens through a series of use cases in three different pilots. For this part, we have selected use cases from the agri-food domain, which we believe it is very interesting because there are many data challenges that are perhaps less explored than in other domains. And we have use cases spanning from food safety to smart agriculture and precision farming. About the platform itself, as already said, this is something targeted to data scientists, and specifically for cases where a data scientist has collected some data sets and creates a workflow or multiple workflows to perform a task. And the challenge there is how to more easily track metadata about workflow executions and about datasets in order to optimize the workflows both during the design phase and also during production. So what the platform facilitates very briefly is to have a unified way to collect metadata for tool executions and for datasets, interlink this metadata and be able to make comparisons, search for workflows, and so on. Then in terms of the toolkit, we have several tools. I will not go through each one here, but just to say that they cover different stages of the pipeline. For example, for discovery, we have a data profiler or a Synopsys data engine for managing big volumes of data. For interlinking, we have tools for entity matching, time series alignment, and fusion. And for annotation, we have tools more domain specific in this case, like for extracting food entities or performing field segmentation and crop classification. But again, this is an extensible list. Just a few words also about the pilots. In the first pilot, the focus is on food safety. Here we have primarily, but not only, textual data like food safety incident reports. And indicative challenges that we are trying to address is how to extract structured information, like the entity that is involved, the product that is being recalled, and so on, in order to make better informed decisions. Then in pilot B, the focus is on early crop yield prediction, which is both a very challenging and very important problem, both at the local level, because in that case, it is possible to provide more actionable information to a farmer to optimize their management, while also at the regional level for providing early warning for food security. And last but not least, in the third pilot, the focus is on precision agriculture, and particularly how to combine multiple different data sets like meteorological variables, agroclimatic indices, and so on, in order to build suitability maps that provide indication about strategic decisions. And with this, I conclude the general introduction to the project. So we will continue now with Vasilis to provide a more in-depth introduction to the platform itself.
Thank you, Dimitri. Is it possible that you can continue sharing the slides?
Yes, sure.
I only have 3, but my
yeah, just a second.
I'm not running Windows, so
yes.
Fantastic. So welcome. I'm Vasilis Samaladas. I'm also with Athena Research Center. I will talk a little bit, continuing what Dimitris has said about the platform. I will focus more on the architecture of STELAR. Can you go to my first slide, please? Thanks. So let me start by placing what the STELAR software is. So STELAR is a knowledge-based lake management system. What is a data lake? Data lake is a data storage system. It is the evolution of the concept that you may have heard of before called the data warehouse. So the idea is that you have an organization that collects data, handles data, and data gets loaded into this facility called the data lake, where not only is it stored, but it is also thoroughly analyzed, thoroughly indexed, in order to make this data, first of all, usable for analysis. So things like data cleaning and format transformation happen. And also the data is indexed so that it is discoverable much later than the time it was collected. A data lake, as the image implies, is about collecting the data, not necessarily in order to use it immediately, but maybe just to accumulate it and use it subsequently. So data ingestion, data collection is one part of the picture of what the data lake is, and also processing. A knowledge lake, in addition to these functions, offers what we call a knowledge layer. This means that the data sets that comprise the data lake are linked together semantically using classes, objects, ontologies, links, all kinds of metadata. And this metadata, collecting it and assigning it to the data sets is quite labor intensive. So the purpose of a knowledge lake is to, as much as possible, automate the collection of metadata, automate the indexing of the data that goes into the lake, automate the cleaning and transformation. And then, of course, the knowledge lake can offer additional search facilities. So searching the knowledge stratum, let's say. And once you identify at the knowledge level what you're looking for, then you can look for data sets that fit your needs. Next, please. So STELAR is quite a complicated data management system. The data layer of STELAR is very important because data can be very high volume. For this purpose, we have employed an industrial standard approach. We use the well-known Amazon S3 protocol in order to provide access to the data stored in the STELAR. On the side of storing and processing the metadata, we have a piece of the system called the data catalog. The data catalog indexes and organizes the data sets and provides search facilities for searching at the metadata level over what is available in the lake. More advanced search and discovery mechanisms are also present. We are providing the ability to search ontologies, knowledge graphs, to also search by informal queries that are analyzed by large language models, and then those searches transferred to the data lake, and several other facilities. I should stress that searching is not just about keywords or concepts, but it is also spatiotemporal. So we explicitly target the annotation of data sets with spatiotemporal information because in the agricultural domain, in the primary sector, this is very important. In order to orchestrate this functionality from a computational point of view, STELAR supports the concept of workflows. We do not necessarily have the same concept of workflows as you could find in other systems. For us, a workflow is a collection of tasks. It's a collection of executions of particular tools. And these tools automatically provide metadata to the data lake when they generate output. The output is data, it is stored in the lake, but the tool also provides automatically metadata that is stored in the lake. In this way, we can find, for example, the lineage, as we call it, of a data set, meaning a data set in the lake has been produced by some other original data that has been transformed in some manner by a tool. All this is automatically registered in the lake and searchable and all of that. And finally, we provide governance. We provide a layer of security and authorization where different users can have different roles and different access rights in order to access the contents of the data lake. From a system point of view, all of this is implemented on top of a cloud infrastructure. It is implemented using a very industrial strength substrate of containers, and it's very highly scalable. It is flexible to deploy and to scale. It is easy to add tools into a STELAR data lake. And it is easy to access because we are using the most standard technologies, APIs and SDKs and so on. Final slide, very quickly. I'm not going to say much about the tools. I'm just going to point out that there are some tools that have been part of the project that are generic. In this slide, you see some of the tools being referred to with a blue color. Like the data profiler, correlation detective, stream summarizer, and so on. And then there are tools that are specific to the agricultural domain. For example, field segmentation. By field, we refer to satellite image processing, weather data interpolation, and so on. These tools are all implemented either inside the STELAR lake, so to speak, or it is possible for a user to have a tool that lives outside. It's a software maybe that is living outside the data lake. However, it is almost seamlessly integratable into Stellar because, after all, what we just need to have is the ability for tool executions to provide metadata to the data lake. And this is something that we support very well. So I don't want to say much more abstractly. It's time to pass on to a demo. And for this, I'm turning to Dimitris Petru, who will demonstrate Stellar for you.
Thank you. So let me share my screen. Okay, I guess you can see my screen, right?
Yes.
Okay. Hi, everyone. I'm Dimitris Petru. I'm a research associate at Athena Research Center. Before moving on to the actual demonstration today, I would like to give you an outline of what we're going to perform. Our main point of interaction today with the Stellar architecture is going to be first the UI console Stellar has to offer, and of course the API with which we are going to interact through the Stellar client. For our demonstration today, we're going to briefly have a look at the UI console, and after that, we're going to execute two tools. Our scenario today and our main goal is that we're going to take some weather data collected from weather stations that, with very much high probability, they have data gaps in between. These data gaps can happen due to power outages to weather stations, to malfunctions, or other problems that might occur during the collection. We're going to produce a completed data set from these primitive records. And we're going to actually use two tools that are capable of doing so. We're going to borrow the missing data interpolation, which is actually a tool that accounts for the coordinates of the weather stations and the missing weather data to produce the final result. And of course, we're going also to use the time series imputation, which uses a family of algorithms to impute time series that have gaps in between. Let me note here that the time series imputation also has an LLM-based version, but today we're going to use the non-LLM approach for this. Of course, the entire process is going to take place on the Stellar platform. And we're going essentially to get the data, the missing data that are stored inside the lake, and run them through the tools and save the results back into the repository. Of course, for external users, we have set up a sandbox instance, which you can actually register today and to try it yourself. For the demonstration purposes, let me switch back to my browser. I guess you can still see my screen, right?
Yes.
Okay, thank you. The main unit under which all entities in Stellar are organized are the organizations. So you can have a single data lake in a multi-tenant setup. If I browse into an organization, I can see that, for example, Athena Research Center has some datasets registered within it, some workflow process executed, and some tools uploaded within the platform. After that, at the heart of the KLMS sits the data catalog, which is actually used in order for providing a structure to the unstructured data that lies within the data lake of the system. The catalog equips the user with a multifaceted search that helps the user narrow down the search result they are looking for. And of course, as Vasily said before, the KLMS, since it's agri-food oriented, we also support spatial search of datasets. So for example, since today we're looking for some weather data from Italy, I'm going to include a spatial filter here over the area of Milano. And also, since these data are provided to us by Abaco, the leaders of Pilot C, I'm going to also filter down the search results for the Abaco organization. To this end, we can see that I received some results. Our dataset of interest today is the Lombardy weather data, which actually contains the missing data records and the coordinates of the weather stations. After that, before moving on to the execution, I need to show you what the tools actually, how the tools are actually registered within the platform. For today, we're going to use, let's say, the missing data interpolation tool. You can see that when the user accesses the console, this tool has been already integrated, and they have the option of browsing the documentation on how to use the tool, what are the expected inputs and outputs, and what execution profiles are available. The execution profiles are a special feature for defining resource usage for resource-intensive tools. Also, of course, for the tools, I have the images, which the image for a tool, when we register it in STELAR, is the actual executable. So actually the source code that will run the tool on the data of the lake. The tools are complemented by the workflow processes tab, in which the user can browse the workflows that are registered within the system, executing a set of experiments using tools from the available integrated toolkit. And of course, for every user that is not very familiar with STELAR or does not originate from the project consortium, we have also deployed the walkthroughs, which are actually small guides on how an external user, fully agnostic of STELAR, can execute a tool from their end and actually interact with the platform. Of course, this is something very administrative, but the administrator of the cluster has the option to manage the users and access the governance rules that control access to the platform's resources. In order to run the execution today, I'm going to use the option of running the task through a Python notebook. So actually, I'm borrowing this notebook from a walkthrough that is available in the platform. And actually, the first thing someone needs to do before moving on with Notebook is installing the STELAR client. STELAR client has also been developed as a complementary part of the platform, which brings a whole abstraction layer for the end user, decoupling them from having to deal with plain HTTP requests. It also offers some very interesting features on handling of data, which I believe data scientists would appreciate too much, since it's very pandas friendly. And let me not waste any more time, and let's run the first block. Actually, what I'm going to do as a first step, I'm going to connect to the lake. And you can see that I successfully established a connection with the lake. This happens, of course, through the API STELAR offers. After that, to save some time, I have already populated the dataset we're going to use. Let me actually search for this to gain a better understanding on how the data are structured. For example, let me open the data we're going to use. So you can see we have temperature information and from 4 discrete weather stations. And at some point, let me find, you can see here that we have some gaps. These gaps, as I said before, may have occurred for different reasons. Of course, here the notebook guides me on accessing the dataset on the console. If I go back, of course, in order to run our tasks today with the two tools we're going to use, we need to create a new workflow process, which we can use to run them on. After that, you can see that I have already created a workflow for this. And if I browse back to the console and into the workflows part, I can search my workflow. So you can see that I have already successfully run some tasks in it. And let us proceed with creating also a dataset for storing the results that I'm going to produce. So essentially the completed weather records. Firstly, we're going to run the missing data interpolation tool. Actually, the client offers a class which you can use in order to define the inputs, the outputs, the parameters, and also have access to the task in order to gain insights on the produced results. So when I actually run this block through my Python notebook, we will see a new task being created under the workflow process I have open in my browser tab. So if I run it, you can see that a new task has been created. And also here, I can also see it being run in real time. So here, when browsing a task, the user has the option to browse the parameters used for this task, the input artifacts actually used for this execution, and what the produced outputs actually are. The task already completed, and if I browse to the outputs of it, I can see that a new resource has been created in the data catalog in my in the dataset I created, which contains weather records being completed. So if I browse to the first column we were looking back before, you can see that probably the numbers with more decimals are the ones that were completed by the tool. And you can see that I have successfully got back a full representation of the weather data. Another interesting feature that STELAR has to offer in terms of executions and linear tracking is tracking on the origin of resources in the data catalog that have been curated by tasks. So for a resource, I have the option to looking back on from what tasks it has been produced. Of course, this can have a depth larger than one. So it means that if those two files were produced by another task, I could have a look at it too, and allows the user to go back and overview the task that has been used in order to produce these complete weather records. Of course, as I was saying before, we're going to also use the time series imputation tool in order to perform the same experiment in a different way. In the same notion, we'll also define some inputs here. So for example, here we have the missing file, which is the same file we used back in the missing data interpolation tool, set the parameters, and my desired destination for the output. If I run this block again, let me run this before, because this task depends on the outputs of the previous one. So if I run it again, probably it's currently running, and I should be able to see it here. So the time series imputation module is now running the experiment using the missing weather data. And eventually, when it completes, I will also be able to have a look at the lineage of the produced artifact. So let's wait a bit. In the meantime, let me say that the log we're seeing here is actually the real-time log the tool is executing on the back end of the platform. So this is actually right now being executed on the high computing on the HPC, and it eventually completed. And if I have a look on its outputs, I can go back to the catalog. Of course, the result is the same. Probably we have some derivation, some variation among the two tools, but we're not be going to perform a comparison on the value of the results. And you can see here that a second file has been populating this dataset. And if again I track the lineage, you can see that I have some more information here. The reason why we have two tasks in series right here is because that the interpolated data we produced back before, we used it as a ground truth for the time series imputation task. In this way, we can compare the two tasks. So if I come back to the workflow process it contained in which I run the tasks, I can select them and compare them. So of course, the metrics for these two tasks are not quite comparable since they are different tools, but among executions using the same tool, I can have a better feedback on how the tasks, on how the metrics differ from one task to another. Of course, I omitted to say back then, but the console also incorporates features for comparing datasets, which are, I guess, a very fundamental feature for data catalog. So I can place datasets side by side and contrast them. And I believe that we come to the end of the demo right now, and we can move on to the testimonials on how the pilots use the platform for their use cases.
Okay, thank you, Dimitrios. So, as he has said himself, we will now move on to the pilots. Babis, we can start with Agrono, just to check if you will be sharing the presentation, or
I prefer you to share.
Okay, then just give me a second.
Yes, thank you.
And let me know when you see the presentation. Okay, I'm guessing it's good. Yes. Yeah. Okay, we can start with Agrono with Babis.
Thank you.
Thank you.
Good afternoon, everyone. I'm Babis Thanopoulos from Agrono, and I would like to share you how the KLMS tools have been successfully used in our pilot, our commercial platform, the Food Akai, in order to strengthen food safety intelligence. We worked across 6 use cases focused on risk prevention, bringing automation, data accuracy, and predictive insights into the food supply chain. Food Akai is designed for the food safety and the quality assurance teams in food manufacturers, as well to other key actors in the food industry. And the benefits of using the KLMS tools are listed here. Automations to improve the validation of data sources and prioritization of the harvesting of selected sources. Continuous model updates in order to improve the risk predictions. Also, the entity extraction helped us streamline the identification of the food-related risks. And of course, through correlation analysis, we reveal patterns across ingredients, suppliers, seasonal trends that may not identified otherwise. Let's go to the next one. So this is an example of KLMS use case about the schema matching and automated ingredient mapping using LLMs. In this diagram, starting from the left side, we have the food manufacturer, the client dataset, including ingredients, suppliers, hazards that are aligned to Food Akai's standardized methodologies. This improves the accuracy of the Food Akai functionality, as well the dashboards that are next to the flow. Specifically, the supplier dashboard detects naming differences like abbreviations and correctly maps the suppliers' names to those that are already listed in the official public sources like the European RASP. Also, the ingredient risk dashboard filters precisely the food manufacturer relevant ingredients, even if they are labeled differently. And also, finally, the last dashboard is about the risk prediction that brings together matched data for ingredients, the suppliers, resulting in a more accurate hazard forecast. This was done at scale, mapping more than 6,800 client ingredients and supplier names directly to more than 15,000 ingredients terms, 900,000 verified supplier names, and more than 2,500 hazard data already listed in Food Akai. All mappings were validated by experts, giving us then speed, consistency, and trust. Let's go to the next one. Okay, and here, just more details about the broader application and impact of this specific use case and how this benefits us. Automating mapping improves food safety protocols and the compliance mechanism. Also, this enables consistent documentation for regulatory reporting. Also, with standardized data across procurement and supply chain systems, AI power assistants can provide results in complex queries immediately. And finally, this could reduce the human errors, also to enhance the traceability and leads to faster and more confident decisions in the risk assessment. To close, I would like also to emphasize that through our work in this pilot, using through the Fudakai platform, we have seen how the integration of KLMS tools creates a solid foundation for predictive, trustworthy decision-making across the supply chain, and significantly how this improves the efficiency of our teams. Thank you.
Okay, thank you. Thank you, Babis. I would now then give the floor to Solveig Blöcher from Vista, project scientist working at Vista. And Solveig, can you hear us?
Yes, I can hear you. Thank you.
Okay, great.
All right. So, yes, my name is Solveig Blöcher. I'm a project scientist at Vista and our internal lead for the pilot B. And within our pilot, we demonstrated the STELAR toolset in two very different use cases where we work at different spatial scales to improve early crop yield predictions, so crop type specific yield predictions. We have large data in terms of multiple satellite tiles, so a couple of 100,000 fields that we do time series analysis for. But for the smaller use case, we actually have a smaller set of fields with information that was provided from farmers to do the analysis. We process nearly a terabyte of satellite imagery from different satellite sources over different regions within Europe and different years. And the STELAR toolset actually allowed us to use those different satellites, to fuse those different data sets together, to use them in different machine learning workflows, such as time series imputation, field segmentation, crop classification, where very different types of algorithms were used to process the data. So we can now use LAI, so leaf area index information, that goes through the time series imputation to get time series that are better in terms of availability, so data quality and data quantity, to in the end, when the data is being fed into a crop growth model parameter, have a better, more reliable yield prediction, which isn't just better, but also earlier within the season. Yeah. So the STELAR KLMS actually allowed us to have a very good end-to-end pipeline to improve risk assessment for single farmers and for larger organizations.
Okay, thank you. Thank you very much, Solveig. Simone, I would now give the floor to you to present Pilot C and APAC.
Thank you. Thank you, Julia. I'm Simone Parisi, and I work as a data scientist in Abaco. And speaking about these tools, KLMS represent, of course, for our product, an important improvement, especially seen from the point of view of a data scientist, because allow us, first of all, testing our algorithms in an easy way, choosing easily the input, the parameters, and so on, and fastly introduce change in the algorithm and in the process. And of course, also for our product in platform, because it can easily performed in various version that can be updated in an easy way respect to traditional ways. About that, for the project, we work in 3 different use cases that reflect the products that are introduced in KLMS. The first of all is the vocational score raster tool that allows a user to input a raster file, to set up a criteria that must be respected by the raster file, and we obtain a score map where it is evidenced the area that respects the criteria that the user introduced in the platform. Of course, the output in our case is then displayed in Abaco platform, cloud platform. But in general, can be, of course, displayed in other ways. The second use case was about the agri-product match, and this tool allows to make a filter and a research in different kind of databases. For example, pesticide database or fertilizer database. The important point there is that the user can, of course, upload his criteria of search and filtering, and in performing the algorithm, we obtain the result that then, in our case, is displayed in also in this case in Abaco cloud platform. The important point there is that we can apply a multi-language approach, so we can use different databases and different criteria in different languages. At the end, we have also the missing data interpolation that Dimitris spoke about before. And the important point there is that the missing data interpolation is something useful also for the another algorithm that is the vintage score algorithm that allows using a complete dataset thanks to this interpolation to forecast the quality of the vintage of a certain year. So in this case, this algorithm is an important task in order to obtain available forecast for the vintage. And in general, to obtain a complete data set is an important point, starting point for the user's algorithm. And that's all.
Thank you very much, Simone. Thank you to our pilots. Now we can move on to the Q&A section, but before that, just to echo what Dimitris has said. So yes, this is the STELAR final event and the presentation of the KLMS, and the demonstration of this system. But it is worth noting that we actually do have a webinar tomorrow with the CrackSense project, so you are very much invited to that as well. So that is a joint webinar with another project, and this is our standalone event. And now I would invite you all, if you have some questions, please feel free to add them in the chat box, or you can unmute yourself. I do assume that a majority is interested in the architecture or the demonstration of the platform. So I will give a minute or so for people. just to point to the chat section where Tatiana, our exploitation manager, did send a short questionnaire that you can fill in. We would be very grateful for that as well. Well, okay. If there are no questions, of course, you can always contact us, our coordinator, Dimitris Koutas, or any of our speakers via email to make things easier. You can find the STELAR info email on the website, and then we can forward this email to our esteemed speakers. Okay, well, since seems that we have gotten to the end of our event, we are very grateful that you have taken your time. We know that it's the time of summer holidays. If somebody has anything else to say as a closing word, please do so. If not, I think that we can end the meeting here. Thank you all for joining.
Thank you, Julia, for coordinating the meeting.
Thank you very much, everyone.
Very much.
Thank you.
Insightful. Thanks. Thank you to everyone. Thank you all.
Thank you.
Bye, everybody.
Goodbye.
Bye. Have a nice day.
Bye bye.